As we move back into applications, try to remember that the solutions that we're finding for differential equations are really predictions about what is going to happen when we set the system going. We're going to be thinking this through primarily with the spring mass system, but also remember that there's a parallel for circuits that is exactly analogous because the mathematics is exactly the same. And what we're going to do is explore what kinds of solutions we get, what kind of predictions we get, as we gradually change the parameters through a simulation. What we're going to be dialing up and down is friction and changes in the frequency, which belong to the corresponding or complementary solution, and the frequency in the F external. So keep those in mind as we go through the simulations. The other thing to keep in mind is what the graphs look like. So that'll be fairly obvious, those will be in front of us. But the more challenging thing is to ask yourself why we're getting certain particular mathematical forms in the solutions, and what do they mean, and why did we get those instead of alternatives. In this window, notice the structure we have. We have y double prime plus a damping coefficient times y prime plus the spring coefficient y, and then we have the right-hand side, which is the external force. Notice that we initialize the external force to be 0 in magnitude, so as if it's not there. In the starting scenario, we have a mass of 1 and no damping, so what we get is a simple oscillation solution. When you find the roots, you'd get a root of 5 times root negative 1, and that translates to a simple cosine sine solution in the complementary part. So again, this complementary solution comes from looking at the ingredients on the left-hand side here. We have the non-homogeneous solution here, but notice it has 0 coefficients because there's no actual external force. So we're going to recap what we saw earlier with the homogeneous. So we're going to keep this external force at 0, and we're gradually going to increase the damping. As soon as we have any damping at all, we lose energy and we start seeing the decay of the oscillations. The oscillations happen, but they're happening at smaller and smaller amplitude as time goes on, and we see that in the complementary solution because it has exponentials, negative exponentials, times the cosine sine terms. And we can dial that up even further. And if you recall, there's going to be a critical damping where we go away from exponential times cosine sine to pure exponentials. That's going to happen at a critical damping level of 10 with the other numbers we have here. We'll sneak up on that, and we notice that most of the initial damping has a fairly profound effect early on. Let's go to 1, and then 1.5, and there we start seeing fairly rapid drop-off in the amplitudes of the oscillations, dictated by e to a larger negative number. Let me go up to 2, and go to 2.5, and 3 even. This is so heavily damped that we'd really only see 3 or 4 bounces before the solution settled down, before the mass just steadied down at equilibrium again, or so close that we couldn't tell. Notice again, though, the solutions do have cosine sines forever, it's just the amplitude has gotten so small it's not obvious or visible. When we get to 5 as the damping coefficient, we have very little visible oscillation, though it's still there in the mathematics. Go to 6, 7, and 8. And by the time we hit 8, there's really only one bounce. Go to 9, and 10 is the magic number where we have critical damping. The graph looks very little different from what we had at 9. It's just the mathematical form of the solution looks quite different. If we go beyond that, then we start seeing an extension where it seems like it's taking longer. This corner of the graph here is getting pushed upwards, and it's taking longer to go down to equilibrium because think of this as a mass in oil. We let it go, it's like sluggishly dragging itself down towards the equilibrium point. And that covers our previously seen homogeneous. There's no one pushing on this mass, it's just being released, and then we see what happens based on the spring force and the damping coefficient. All right, we're going to dial our friction back down to 0 and think what that'll mean. With 0 friction, we get the oscillatory solution. We're now going to set up an external force, which has a frequency of 1 radian per second and an amplitude or force strength of 10 on it. What that means is we're going to imagine this mass and we're going to start pushing on it. But if you notice the frequency here, this is a fairly high frequency, so these oscillations are happening fairly quickly. When we have a number like 1 here, it means that we're going to push down and then push up and then push down, but it's going to be much slower. A lower number means lower frequency. It's going to be much slower than the actual natural vibrations. And the solution is going to be a combination of this solution and something with cos and sine of 1t. So ask yourself, what would it look like if we added up a high frequency cos of 5t sine of 5t thing and a cos of t sine of t thing? Let's try that and see what we get. Well, that's interesting. We start getting something semi-regular. We see that the magnitude of the oscillations is much bigger. We started here, and because we're forcing this thing with a fairly large 10 Newton force that's coming on and off, we actually get some strong response from the system, but it's not really well structured and certainly not something we could have predicted in any detail, though saying we have 2 different frequencies and seeing a low frequency thing, which is sort of this arch this time from here to here, and then a high frequency thing in between, well, maybe some sort of jagged thing where we push on this mass out of sync from the way it would naturally oscillate would lead to this kind of result. Note the form of the solutions though. We did not change the left-hand side, therefore the left-hand side, the complementary solution, is just cos 5t and sine 5t's. The right-hand side, which is sine of 1t, is going to have a differential family of cos and sine, and this differential family is cos of 1t and sine of 1t. So the total solution is the sum of those 2 ingredients, so it's like adding 2 graphs, and we get this sort of jagged compilation. Now what if we try some different frequencies in here, like a 2 or something? Well, again, we get that sort of surprising jagged correlation between the 2 things. If we chose some odd number like 2.252, we get something that looks a little less periodic because these 2 things don't line up with their frequencies. We could also try 1.76 or something. We see unpredictable responses, just like you'd expect if we had a mass and we started pushing on it and it wants to oscillate at this frequency of 5 radians per second, and we're pushing at some other weird rate. Another analogy, if it helps, is to think of pushing a friend on a swing. If you push them in sync, then you build up some energy. If you push them sort of randomly when they were swinging back and forth, then you wouldn't get any buildup, and you might get this kind of strange, oh, where am I going behavior in terms of the predicted motion.